Alright, so let's take a look at some questions all about the process of magnetization, demagnetization, and how hard it is to do those processes. So first of all, we've got a magnet, or a permanent magnet I'm assuming, brought near metal bars X and Y. When we bring it near X, nothing happens, and when we bring it near Y, we get them repelling each other. So before we actually answer the specific question, let's look at the information you're expected to use to answer this question. So there are essentially three types of materials we can consider here. We can think about soft magnetic materials, and if you bring a permanent magnet to a soft magnetic material, that material will align itself, or its domains will align itself with the external magnetic field, and it's attracted to the magnet. It doesn't matter if we bring the north or south pole towards it, we get attraction. If we have a hard magnetic material, they will not be affected, or their domains, sorry, will not be affected by the permanent magnet. But if it's already magnetized, then it could either attract or repel the permanent magnet, depending on how it's aligned. And if it's a non-magnetic material, nothing whatsoever will happen when you bring a magnet towards it. So we can see straight away that X is a non-magnetic material because nothing has happened. So we can get rid of answers C and D straight away because iron is a magnetic material. It's a soft magnetic material, so that doesn't match up with X. Now, Y must be a permanent magnet or a hard magnetic material because soft magnetic materials do not repel like permanent magnets. They always attract them. So we can eliminate option B because iron is a soft magnetic material, so that doesn't make sense. So Y is clearly already a permanent magnet, and it's got its north pole pointed towards the north pole of the permanent magnet, which is why they repel each other. Okay. So a magnet is brought near some metals. It induces magnetic poles in the metals. Which diagram shows the poles induced when a magnet is brought near to unmagnetized iron and unmagnetized aluminium? So iron is a soft magnetic material. Aluminium is a non-magnetic material as far as I'm aware. So again, we've got the same information we're kind of using for the previous question. So if we bring the permanent magnet to iron, we should get the iron will turn into a magnet in the same direction as the external one. So we can see that option A, that hasn't happened. We've got a magnetic field in the opposite direction and it would repel, so that doesn't make sense. Option B, same thing. We would induce a north pole in the closest side to the magnet, so again that doesn't work. So it must be C or D. Aluminium is a non-magnetic material, so I wouldn't expect anything to happen, so we're going to get option D. And if we think about it, even if aluminium was a hard magnetic material, not much is likely to happen anyway. So even if it was hard, this would still work. But the key is it's not soft. Okay, so we've got two rods, X and Y, that look the same. And we're going to bring a permanent magnet towards each. And we've got the results. So P and Q, it attracts both. So we can group those together. So if both ends attract, that's telling us we've got a soft magnetic material here, which means it means it's not a magnet, because if it was a magnet, then one end would attract and one end would repel. So rod X is not a magnet. For the rod Y, we've got one end attracts and one end repels, so that's not a soft magnetic material. That must be a hard magnetic material, and it must already be magnetized. So we're looking at a permanent magnet there. So the answer is rod Y is magnetized. Okay, so a plotting compass is placed at each end of a magnet. Which diagram shows the positions of the pointers of the plotting compasses? So let's think about the rules we have to use here. So for a permanent magnet, magnetic field lines always go out of the north pole and into a south pole. So therefore the compass should point into one end and out of the opposite end. So A and B don't make sense because they're not pointing into or out of the end. C, they're both pointing into the magnet, so that doesn't make sense. So it must be option D. We've got one going in, which must be the south pole on the left, and one going out on the right, which must be the north pole. Okay, so we've got 2 pins onto a magnet as was shown, and the student removes their thumb, which diagram shows the positions of the pins and the poles induced on them. So all 4 diagrams indicate that the pins have become a magnet. So we're not dealing with a non-magnetic material where they would just fall off here. So if we've turned them into a magnet, they're going to be attracted to the North Pole. So we must get a South Pole at the top, which means we must get a North Pole at the bottom. And if we've got 2 North Poles at the bottom, those are going to repel each other, so they're going to get pushed out, which is clearly option A. Or the other way of thinking about it is if you put 2 magnets parallel with their North Poles in the same direction, they actually repel each other, and you can try that experimentally. A piece of soft iron is placed in a coil. The switch is then closed. What is the condition of the soft iron when the switch is open and when the switch is closed? So iron will not have a magnetic field if you haven't done something to magnetize it. So if we've got no current in the coil, the iron is going to be demagnetized. Its domains are going to be aligned all over the place. So with the switch open, we expect it to be unmagnetized. Whereas when we close the switch and run a current, the domains will line up with the magnetic field of the coil, and so then the iron will become magnetized. So we can clearly see it's going to be option C. So a magnet is placed in a coil connected to electrical supply. What is the best way to demagnetize? So it's a magnet we've created here. So we've got all the domains lined up at the moment. So we want to essentially make all the domains point in different directions. So DC isn't going to get us anything, because DC, it might change the alignment of the domains, but they would still all be lined up with each other. So it'd still be a magnet. So DC is not going to get us anywhere. AC is going to sort of flip the domains between directions. So 1 second they'd all be aligned one way, 1 second they'd all be aligned the other, if we just left it in the magnetic field. But if we slowly remove it, we actually get them all lined up in lots of different directions, and we get as demagnetized because we've made all the domains in different directions. Okay, so the diagrams show a magnetized piece of steel being moved slowly to the left, which diagram shows the best method of demagnetizing the steel. So first of all, A shows DC, that's not going to demagnetize it. B shows AC, and we're moving it out, the 2 things that we need, so B works. C and D, they might well change the alignment of the domains, but they're going to still have them all lined up in the same direction, so that wouldn't demagnetize it, it just might realign the magnetic field. Draw carefully the magnetic field lines around the following arrangements of bar magnets. So the rules I'm going to use here is field lines always go from north to south, and the field lines must start at a north pole and end at a south pole. So here would be the field for this set of magnets. We can see the field lines outside the magnets going from north pole to a south pole, and it must form what we call a closed loop, so it must go from a north pole to a south pole. That's always true. Inside the magnets, the fields actually go from south to north, but we won't worry about that too much. A second diagram that we're going to draw, we've got south pole to south pole. So here what we get is, again, although some of these field lines have been shown as being incomplete, that just means they've kind of gone out of the scope of the diagram. Those would actually continue, but we end up with no field lines in this middle section here because they can't go from south to south, and field lines cannot cross over one another. So we end up with this region of nothing in the middle. Okay, so that completes this video looking at some problems with magnetization.